Okay, cool. So we begin with section 7 of L&L's mechanics, and this section is titled Momentum. Now, here we're originally taught conservation laws as facts. You know, the fact that energy is conserved, which I was able to prove last video. Um, this video is more so on proving how momentum is conserved. And it's not just necessarily because Newton said so. Now, the real reason is symmetry. If I were to start a clock 10 seconds later and nothing about the laws of physics changes, then energy must be conserved. If I also were to shift the entire universe, let's say 1 meter, 10 meters to the left, and physics does not care, then I can only assume that momentum must also be conserved. Thus, this is what I will be attempting to prove in this video. So, we can do this by stating that we have a infinitesimal change in our Lagrangian, which is going to be stated as the sum over A of del L del RA times the infinitesimal change del RA, right? And if we say that our radius vector becomes our original radius vector plus the infinitesimal change, I'm going to call that epsilon, then we can see from that formulation that it is just equivalent to epsilon times the sum over A of del L del RA. Now, stemming from the original laws of the Lagrangian and Euler's-Lagrange, or the Euler-Lagrange formula, we have del L del RA equal to 0. Now, the only way that this can hold in our assumption here is, since our infinitesimal change is not going to be 0, the only way that it holds is if this term is 0. So we now have del L del RA minus d dt del L del VA equal to 0 from the Euler-Lagrange formula. And if del L del RA equals 0, that must also mean that d dt of del L del VA equals 0. Thus, this term here must be constant. And from basic formulation, if we were to take the derivative of velocity, of the Lagrangian with respect to velocity, and our only term in the Lagrangian containing velocity is 1/2 ma va squared. Taking this derivative, we get just ma va, which we know from basic physics is the definition of momentum. Hence, momentum is conserved. Now, another really cool thing that is also formulated from this Euler-Lagrange statement is we have del L del RA minus d dt del L del VA equals 0. So we have minus P and del L del RA. Now, the only term in our Lagrangian that contains only specifically the radius vector is going to be our potential energy. So thus, we have del U del RA minus P equals 0. And It should also be noted that this is not just p, it's p dot, because we took the time derivative of momentum. And rearranging, we have del u del Ra is equal to p dot. Now, we know from an earlier section that the force acting on the eighth particle is equivalent to del u del Ra, negative del u del Ra. So we can also state that this is equal to the force. Hence, our individualized force is equal to the time derivative of momentum. And these are Newton's laws emerging from our proof that if we have a infinitesimal change to the radial vector in the Lagrangian, our systems come out with these conservation laws. And that's pretty much all Landau was trying to state in this chapter.